Feel free to slow me down or ask questions when they come up. So this is what we're going to be doing today. First, we'll just outline characteristics of games and best responses, go through strategies, the concept of Nash equilibrium, and if there's time, repeated games. So these slides are from last year, so forgive me if I'm a little rusty on any of this. Alright, so a game has 4 characteristics, generally speaking. You've got a set of rules, a set of players, which is commonly denoted as N, a set of payoffs for each player, so that's U, and then the subscript over here, the I, indicates you're dealing with player I, and then a set of strategies or actions for each player, which is commonly denoted as alpha subscript I, right? So in economics, we assume that players are rational and thus choose to maximize their payoff given the strategies available to all players. Hence, we assume that each player plays their best response strategy in equilibrium. So that's a concept that you'll become very familiar with by the end of the course. The best response strategy represents the best course of action for a player given... the best response strategy represents the best course of action a player can take given actions available to all of the players. So another concept is the idea of a dominant strategy. So we're saying alpha I is strictly dominant for player I if it is the player's best response strategy. If it is the player's best response for every strategy. So AJ, where J is not equal to I, is the idea. So these are the player's other available strategies. Available to another player, J, so I just screwed that up, never mind. It's probably better to just read off the slides. So the idea is that this strategy, AI, achieves the highest possible payoff for player I, no matter what, and is therefore always the best response. So if you find a strictly dominant strategy in equilibrium, the player has to play it, so that's what you want to look at. In contrast, the strategy is strictly dominated. If it is never the best response to any possible strategy, so it's never played in equilibrium if it's strictly dominated. So yeah, this is just repeating what I said. A strictly dominant strategy is always played in equilibrium and you should look for it. You'll notice that there's a lot of exclamation marks in these slides because I had a lot more enthusiasm a year ago. No one thinks it's funny? Alright, cool. Alright, so it was an exciting time in late 2015 for Steve. Now I'm all kind of washed up and cynical. Anyway, so here in this matrix we have 2 players, each with 3 strategies, for a total of 18 possible payoffs, or 9 each. So these are player 1 strategies. Player 1 can go up, middle, or down. Similarly, player 2 can go left, middle, or right. What we've got here, this 3 is the payoff for player 1. This 7 is the payoff for player 2. And together, this is what each player gets if player 1 plays up and player 2 plays left. So that's just how to read one of the tables. So payoffs are given at the intersection of the possible strategies. For player 1, alright, so now we're going into what's strictly dominant. So for player 1, M1 strictly dominates both up and down, and it is therefore the dominant strategy. So how the hell does that work? What you do is rub this out, so you can't rub it out, never mind. If you look at player 1, if you look at this row here, the up row, you can see that if player 2 is playing left, so now imagine we're just locking in and only looking at this column. Player 2 is playing left, then player 1 is best playing M1. Why? Because 5 is bigger than 3, so M1 is clearly better than up, and it's also better than down. If we lock in instead, player 2 is definitely going to play M2. Then player 1 is still better off playing M1 because 13 is better than 4, and 13 is better than 2. And then similarly, 4 is better than 3, and 4 is better than 1. So no matter what player 2 is doing, player 2 could be playing left, middle, or right. Player 1 is best playing M1. and that's why M1 is strictly dominant, or it strictly dominates both up and down. Does that make sense? I said up, down, and dominant like 15 times, and if you're not following, that's cool, just let me know. So for player 2, left strictly dominates M2 and right. So let's look at that. So if we look at player 2, we're looking at player 2's left strategy now. So say player 1 is playing upright. So locking it in this way, we're now locking in player 1's action, so we're only looking at this row. Player 2 can get 7, can get 6, or can get 1. Clearly 7 is the highest, so left is the dominant strategy. Left is dominating M2 and right. If player 1 is instead going M1, player 2 can get 10, 0, or 2. Clearly 10 is the best. And then finally player 2 can get 4, 3, or 2, given that player 1 is playing down, and clearly 4 is the highest there. So left is player 2's strictly dominant strategy. So this kind of reasoning where you sort of lock in one player's action and then fool around with the other player to see what their optimal response is, that's how you solve these sort of quote table games. Yeah. Okay, so a weakly dominant strategy is the more common case. So this strategy, alpha I, is weakly dominant if, regardless of what any other players do, the strategy earns player I a payoff at least as high as any other strategy, and the strategy earns a strictly higher payoff for some other strategy profiles. That'll make more sense in a minute when we go through an example. But basically, when you're just looking at the table, for example, we saw, okay, cool, 13 is better than 10, right? But if instead we had 13, and then the other payoff was 13, and the other thing is 12, then you could say this is weakly dominant, because it's the same, it's as good as this, but it's definitely better than that. We'll go through it and make more sense, hopefully, if you're not following. So a strategy is weakly dominant if it is always at least as good as any other strategy for any profile of other players' actions, and is strictly better for some profiles of other strategies. Much easier to explain with an example, obviously. So one more time, hands up if you took game theory at some point. Okay, cool. So I didn't do theory before taking this course, so it's fine. If you didn't take game theory, you're good. But if you did take game theory, you're like extra good. So everybody's winning. Alright, so here we have two players, player 1, player 2. They both have three strategies, same as before. Player 1 can play up, middle, or down. Player 2 can play left, middle, or right. So for player 1, down weakly dominates M1. Alright, so let's look at that. So here we're looking at down for player 1. Now let's lock in left. So now we're saying player 2 is definitely playing left, okay? So player 1 can play down and get 6, can play 2 and can play middle and get 2, or can play up and get 3. Clearly 6 is the best option. We move across here. Player 1 can play down and get 4, can play middle and get 4, and can play up and get 7. Right. Okay, cool. And then if you look over here, player 1 can play down and get 5, M1 and get 3, and play up and get 1. So what's the idea? The idea is that down weakly dominates M1. Why? Because 6 is better than 2, 4 is as good as 4, and 5 is better than 3. Down does not weakly or strictly dominate up, because here we can see that 7 is in fact better than 4. So we can only say that down weakly dominates M1 for player 1. If instead this was a 3, then it would strictly dominate M1. For player 2, we can see that left weakly dominates right. So now if we were to say, okay, cool, we're locking in player 1, we're saying that player 1 is definitely playing up. We can see player 2 can get 5, 5, or 2. If we lock in instead M1, player 2 can get 4, 1, or 4. And finally, if you lock in the last one, down, you can see that player 2 can get 2, 4, or 2, right? So the idea is left weakly dominates right, because here 5 is better than 2, 4 is as good as 4, and 2 is as good as 2. So a Nash equilibrium occurs when both players play their best response strategy simultaneously. So a Nash equilibrium occurs at the intersection of the best response functions, which you'll see later. Thus, both players are doing the best they can and are acting rationally. So that's what economics thinks everybody does, even though it's fairly obvious that we don't behave rationally in a lot of ways. So a requirement or a condition for Nash equilibrium is that no player has an incentive to deviate, and really this is the main one you're looking for when you're trying to find the Nash, right? That is, no player can increase their payoff by deviating from their current strategy. So basically, this is, I'd say, the main one for Nash equilibrium when you're trying to find it. There's no incentive to deviate, and the person cannot increase their payoff by changing their strategy or their action. So note that if both players have strictly dominant strategies, then the Nash is always at the intersection of their strictly dominant strategies. You sure there are no questions? Because I'm just flying through this. We're all going to get out of here pretty early. Okay. How about a smile? Can I get something? I see a thank you. Beautiful. If I had the authority, I've said this like every shoot in some shoots, but if I could give you marks for that smile, I would. I just have like no power, so I can't. So solving a normal form Nash equilibrium game is very easy. It's a fairly simple algorithm. So you select a cell in the table. So that's like a row column combination. You lock in the strategy. You lock in the actions of player I. You search for profitable deviations from the other player. If you find a profitable deviation, it's not a Nash. If you can't find one, then you lock in the actions for player J and you search for profitable deviations for the other player. If you find one, then it's not a Nash and you move to the next cell. If you don't find one, then assuming there are only 2 players, then you found at least one of the Nash's equilibriums. Okay, so let's do this one. This one's fairly easy. It's just your 2x2 game. So first, let's lock in player 2. All right. Let's say player 2 is definitely going to play left, and then player 1 can play up or M1. So if player 1 goes up, he or she gets a payoff of 3. If player 1 goes down, or rather M1, then player 1 gets a payoff of 1. Clearly, player 1 prefers up. Now let's lock in player 1. Player 2 can play left or M2. 9 is clearly better than 3. Since there's no incentive to deviate, up left is the Nash equilibrium profile, and you get payoffs 3 and 9, right? See how that works. Let's move over here. Let's look at here to sort of show you how it doesn't work. So now let's lock in player 2. Player 2 is definitely playing M2 now. Player 1 can go up and get 0, or go M1 and get 2. Clearly player 1's going to go M1. Now player 2 can go M2 or left. Clearly player 2 has an incentive to deviate over here because 3 is bigger than 2. So we know that this is not a Nash, and then we'd start over here. And you basically just rinse and repeat the procedure until you find the Nash. There is not always a pure strategy Nash in any game. There's always a mixed strategy Nash. Has anybody seen the movie A Beautiful Mind? Yes. Did you guys just think it was terrible? No? Did you guys think it was good? Oh, it was terrible. I was like falling asleep. Everyone's like, oh, you have to watch Beautiful Mind, Game Theory. And I watched it. I was like, man, this sucks. Like, this is a terrible movie. Anywho. But apparently I have terrible taste in movies. Yeah, I get a lot of shit. My girlfriend hates my taste in movies. So, like, we always play scissors, paper, rock to decide who's deciding which movie you'd watch. And then I always lose. Like I'm 90% of the time I lose, and it's ridiculous. Like I should, it's scissors paper rock. Like how can you lose that many times anyway. Uh, and I'm randomizing too. I'm doing what game theory tells you to do, which is just play everything 1/3, right? They can prove that you're supposed to play 1/3, and I'm doing it, and it's not working for me. She says she has a system, right? And I'm just like, what the hell system do you have? How do I adopt it? So now every time we play, I'm just like staring at her and like, I'll play rock and then she'll play scissors and I'll be like, okay, cool. Every time you play rock, she plays scissors and then she plays paper on the next round and then she'll just play rock and I'm just like, so yeah. Anyway, it's cool. I've had a good night's sleep, guys. Anyway, moving on. So again, 2 players, 2 strategies. Payoffs are given in the table over here. Now, we have 2 Nash equilibria. Also, it's Nash equilibria, not equilibriums. I got in some trouble for that last year and was teased a lot for being illiterate, so it's equilibria. That's the plural of equilibrium, in case anybody was wondering. Alright, so let's find them, right? We lock in left for player 2. Player 1 can go up, M1 or down. Clearly M1 is the go because 98 is by far the highest. Now we lock in M1. Player 2 can get 4, 12, or 4. Clearly M2 is the go, so we're over here now. We lock in M2. Player 1 can get 32, 7, or 4. So there is no incentive to deviate here, right? So M1, M2 is one of the Nash strategy profiles. Okay, and then if we lock in right, you can see that player 1's going to drift down to here, and then if you lock in down, player 2 can get 2, 4, or 77, so clearly this is another Nash, right? Okay, so now we've got the mixed strategy, Nash equilibrium. Scissors, paper, rock's a great example of this crap not flying, but anyway. So far the strategies available to the players I have shown you have all been pure strategies. Now we're looking at mixed strategy. So a pure strategy just means that you're definitely going up, right, down, left or right, whatever. Mixed strategies are another option. It basically means that you play a strategy with some probability. That is, you randomize between strategies, playing each one with some probability. So the mixed strategy Nash equilibrium occurs when both players randomize between strategies such that both are indifferent between actions. Notes, pure strategy Nash equilibrium is a special case of mixed strategy where the probability you play each strategy is 1 or 100%. So how do you solve these? You write out P and 1 minus P. Generally, this is for player 1. Q and 1 minus Q for player 2. Decide what to go over. Go after first. You can get P, you can get Q. It doesn't matter. You get the expected value of player 2's payoff given player 1 plays left. You do the same thing for player 2, given that player 2 is playing right. And then you set them equal, and that's how you solve for P. And let's do an example. I'm going to draw the table again. So how'd you guys find the problem set? Honest feedback. Somebody want to talk about it? Did Emil give the problem sets back in the lecture? What do you guys think? How was it too hard? Was it too easy? Was it fair? Was it just right? It was fair? Cool. Alright, so how do you do it? You basically say, okay, for player 1, player 1's going to play up with probability P and down with probability 1 minus P. Player 2 is going to play left with probability Q and right with probability 1 minus Q, right? So let's go after Q first, it looks like. That's what we're doing. So in order to go after Q, you would say the expected value or the expected utility of player 1, given that she is playing up, is going to be 3q plus 0, 1 minus q. Where the hell did that come from? So what we're doing is we're locking in player 1 playing up, so we're looking at this row here, and then we're saying, okay, if player 2 plays left and player 1 plays up, then player 1 gets a payoff of 3, and player 2 plays left with probability q, so that's where the 3q comes from. Player 1 is going to get payoff 3 with probability q, and then similarly, player 1 is definitely playing up, so if player 2 plays right, then player 1 gets a payoff of 0 with probability 1 minus q. That's where that comes from. Three Q. So now we do the other thing for if player 1 is playing down, and that's going to be Q plus 2, 1 minus Q. Once again, where is that coming from? If we say player 1 is definitely playing down, then player 1 is going to get a payoff of 1 with probability q and a payoff of 2 with probability 1 minus q. And then we're trying to find the probability, so, well, basically I'll just show you how to do it. So this is the expected utility of player 1 given that she is playing down. So you just set them equal, and then you just solve for q. And that's how you get the mixed strategy in these kind of games. Piece of cake. So one thing I would note, I should warn you guys about, if you're not familiar with this kind of stuff, it's a little bit counterintuitive in the way that Q is the probability that player 2 is going to play left, right? And right now we're just fooling around with player 1's utility. So when you're solving these things, you kind of have to go backwards, right? So if you want the probability that player 2 plays left, or Q, you have to use player 1, and it's kind of backwards like that. And it can be weird to get your head around if you're not familiar with how to do it, so just bear that in mind. Now we're going to go after P. What the hell is P? P is the probability that player 1 plays up, which means we have to deal with player 2's expected utility. What color do you guys like? Purple? We can get some purple going. Alright. So this is the expected utility that player 2 gets given that she is playing left, and that's going to be P plus 3, 1 minus P. Where is that coming from again? If player 2 we know player 2 is just definitely playing left, that's our assumption. So player 2 gets a payoff of 1 if player 1 plays up with probability P, and player 2 gets 3 if player 1 plays down with probability 1 minus P. So that's where this comes from. Again, we just do it given the other action. And then all we have to do is make it a bit easier. Okay, and then we just set them equal, so it's 3 minus 2p equal to 2 plus p. And we get 1 is equal to 3p, and then 1/3 is equal to p star. So that's how you get p and q, and then obviously 1 minus p and 1 minus q is just, 1 minus p and 1 minus q. So, did I get it right? Good. So a sub-game perfect Nash equilibrium, or SPE, is what we're dealing with now. Here we look at games that occur over time in different time periods. For SPE, we will look at game trees, and they're referred to as extensive form games. A tree has multiple paths you can take. So a path is kind of like a branch in the tree. A tree has decision nodes, much like in life. So the decision node is what connects the branches, and that they indicate possible decisions for the players. An information set is a set of possible decision nodes that the player might be at in the game. Thus, if your information set contains more than one node, you have no idea where you are. So if you have full information, then you should know where you are in the game tree. There's an example tree coming that I stole out of Toru's game theory course coming up. For those of you who remember, they're drawn terribly, but that's okay. So perfect information means that we have one node in our information set. We know where we are on the tree. If you have more than one node in your set, then you have no idea where you are, and that's referred to as imperfect information. Imperfect information is denoted with dotted lines or a circle between nodes. What is? I thought there'd be a tree there, but you'll see it in a sec. Alright, so a subgame is the part of a tree beginning from a full information set, a single node. Payoffs on a tree are determined by a sequence of actions played until the end of the tree is reached, which is referred to as the terminal node. SPE is solved using backwards induction, which is very common in this course. So basically you start at the smaller subgame and you just work backwards. A set of strategies is a subgame perfect Nash equilibrium, or SPE, if no player has an incentive to deviate from the SPE strategy in any subgame. So throughout the whole tree they've got no incentive to deviate all the way down. So SPE is a refinement of Nash equilibrium that removes non-credible threats. So SPE removes non-credible threats. This is the game tree we're looking at. Since we got a minute, I'm gonna redraw the. Actually, no, I'm not. Okay. So, where are we at? No, you know what? I am gonna redraw the tree. All right. So here is my fresh-looking tree. Woo! Damn, that's a Steve, is what that is. All right, so what have we got here? This thing, that's a Steve Young original, 2016. In case anybody, if you'd like to purchase my tree, it's available. I've got my own YouTube channel now. In case anybody was wondering, with like 3 views on my IO videos. So what are we looking at here? This circle denotes imperfect information. So here's player 3 at this stage in the game, and player 3 has had a big night out in Canberra and has no idea where he or she is. So he could be here or he could be here. He's not sure. At the end, where you can see the payoffs here, this is the payoff for player 1, player 2, and player 3 in order. These are the terminal nodes. These really awesomely drawn straight lines are the branches, and the dots indicate the decision nodes, and then by a decision node you can see P1 means it's player 1's decision node, so that's how that works. So what do? We start at small subgames and work backwards. So first we're going to start over here. So it's player 1's decision node. What does player 1 like? Player 1 can have 2 if he goes left, or 3 if he goes right. He's going to go right, so you draw a little arrow like that. And then we move backwards over here, and then player 2 can decide whether to go left or right. If player 2 goes left, then player 1 will go right, and then player 2 is going to get 1. If player 2 goes right instead, player 2 can have 5. Clearly, player 2 would go this way. Right? Now, moving down here, this imperfect information generates a massive pain in the ass for us, because you can't condition your move on somebody else's move, because player 3 doesn't know what player 2 is going to do. So, how do we deal with this? We have to treat it like a simultaneous game, and then draw out your standard sort of matrix table game. So here we've got player 2 can go left or right, and player 3 can go A, B, or C. So that's where these are coming from. And then you just fill in the payoffs. Where are these payoffs coming from? Payoffs are coming from the terminal nodes here. So for example, if player 2 was to go left and player 1 was to go A, then we'd be at player 2 going left, player 1 going A, and the payoff would be 2-2. As you can see, for player 2 and player 3, that's their payoffs, 2-2. Similarly, if player 2 were instead to go right and player 3 were to go A, we would go right A, and then it's going to be 3-1, which is here. So that's where these payoffs are coming from, right? You stick them in a table, and then you solve it using your Nash equilibrium concept. So what's the best way to do it? Let's lock in player 2 as going right, and then player 3 can go A, B, or C. If player 3 goes A, he gets 1. If he goes B, he gets 2. If he goes C, he gets 3. So clearly this is the better option. Now we lock in player 2, and we say player 1 can go left or right. Player 1 goes left, he gets 3. If player 2 goes left, he gets 3. If he goes right, he gets 2. Clearly this is the better option. And then we lock in player 2's actions again, and then player 2 can get 2, 1, or 3. So clearly this is the Nash, right? Here neither party has an incentive to deviate, and that's at left C. So we can draw it on here, C and then left. And then the last decision node is over here for player 1, where player 1 chooses to go left or right. If player 1 goes left, then he's going to end up here with a payoff of 0. If player 1 goes right, then he's going to end up down here with a payoff of 4. So clearly he's going to choose to go right. And that's how you use backwards induction to solve the extent